Good afternoon, everyone. Welcome to the General Assembly of the European Geosciences Union. Thank you for joining us here in Vienna or elsewhere if you're watching us remotely. I'm Barbara Freire. I'm the EGU Media and Communications Manager, and I'll be your host at the Press Center this week. Feel free to come to me or to one of my press assistants with any questions you might have, or if you'd like to book one of the side rooms we have available for interviews. We have organized 9 press conferences for you this week, which include a period for questions after short presentations by the speakers. Journalists watching remotely can ask questions using the chat feature on the video streaming page. Press releases or other documents relating to the press conferences will not be distributed by email by me, so please check the page media.egu.eu/documents regularly throughout the week because it will be updated. The first press conference is on the Dawn mission at Ceres, when we have new results from NASA. And I'll give the floor to Christopher Russell, who is the principal investigator for the mission, who will take care of the remaining introductions. Chris.
Thank you, Barbara. It's a pleasure to be here, and it's a pleasure for us to have our spacecraft now in orbit around Ceres. Vesta was our first target. We left Vesta in September 2012. In the last 2.5 years, we've been thrusting with our ion thrusters and sending us over to Ceres, and now we've slowed down and gone into orbit. On the screen, you can see a picture of Vesta in the foreground, and that is Ceres with its 2 bright spots in the background, and now we're in orbit around that body. When we think of Ceres' place in the solar system, we compare it to some icy moons of Saturn. Enceladus, that one on the left, which is very bright, albedo of close to 1. It's got essentially snow on the surface, so we lost. Okay, and this is a very, very sensitive device up here. Anyways, and Dione, another moon of Saturn, very bright, and it's an icy. And Pluto is our last comparative object. It's another dwarf planet, as named by the IAU. And what we're doing this year in the year of the dwarf planet is finding out what a dwarf planet really is. It's not necessarily the same as the IAU was thinking about, but we will learn that with the Pluto mission and with Dawn. Now, Ceres, you can see, is intermediate in size between Enceladus and Dione, those 2 icy moons, but it's darker, and that darkness tells us it's not just a simple icy body like those other moons, and its density is not as close to that of water. It's about twice that of water, so we know that it's got a lot of rock in its interior. So we're expecting Ceres to be about 1/4 made of water or water ice, and then 3/4 to be rocky. So here's the interior as we believe from theory and from thermal evolution models it to be, that in the interior, with that arrow saying anhydrous silicate, it's got a dry rocky core, and then the more light orange is a region we believe is hydrated. It's wet rock. Then there may be some water, some liquid water in there, and on the outside we're expecting there to be an icy shell of pure ice covered with the dark material that we see in those in that picture that I just showed, and that is stuff coming in, maybe some material derived from the interior that has got out on on the surface. So we think there's some ice around, but the outside is quite dark. Now, on our approach, we have this unusual path. We didn't plan that in that way. We came in a little bit more smoothly, but we had an interruption in our thrusting, and so we got into this looping orbit. And that looping orbit, after we got into the orbit on March the 6th, took us over the dark side of Ceres. And so we haven't had any images until just on April the 10th, when we got a little sliver of a light across the terminator, and there was nothing surprising in that data because there was just a little bit of data. We'll do that again on April the 15th, and then we'll go into orbit, into that first science orbit, which we call rotational characterization 3, and by early May we will start bringing down that science data. We have been able to, with the images we've taken thus far, count craters and identify craters. This particular map shows all the craters greater than 40 kilometers, and we see some evidence here of highly cratered regions. That's mainly in the north on this diagram, and some regions that are less cratered. And when we compare the size of the craters we see on Ceres with those on Vesta, we find that we're missing a number of large craters, the number that we would expect. So there's something that we've got to learn about when we take the next set of science data to try to understand why we're seeing regional variations in the crater density, and especially a lack of the largest craters that we expected. This is RC3, the rotational characterization 3, and on the right-hand side of that diagram, there's two dark images there of, and that's what we think we will see when we take pictures from that area. So why would we want to do that? Well, we want to do that because the sun shining across the limb might give us some scattering off a plume, if there is any plume. So we'll be looking for plumes like the Herschel Space Observatory reported. They didn't really see plumes per se. They saw water vapor, but they interpreted that it could be coming off in a plume. And then we will circle around and then go over the limb and then get over on the day side and see the brighter images, and we'll get much better coverage of the surface in there, and then we'll come around again on the other side. Now, after we do that, we're going to lower the orbit into the survey orbit, and that is optimized for the visible and infrared mapping spectrometer. We'll do 7 cycles of one orbit each, and then do that over 22 days. We'll also take framing camera data, limb images with the framing camera, and some color imaging to give us a coarse geologic map. Later, we'll go down further to what we call the high altitude mapping orbit. In that, we get global coverage in color. We get stereo imaging. That picture on the right at the top tells us that in that sort of reddish purple, we are getting more than 5 images of each of those spots. Our worst resolution on this particular picture, we get 2, and that's the minimum that we use for topography. But this gives us good topographic coverage over most of the planet. And then the lower left image tells us that we complete the imaging requirements for the mineralogy investigation. The last and lowest orbit is LAMO, Low Altitude Mapping Orbit, and that mesh of orange there tells us that we're getting a very fine coverage of the surface. This is where we get our highest resolution and we take our most data. We not only do imaging here and some VIR spectrometry, but we get good gravity data at this low altitude, and we use the gamma ray and neutron spectrometer to give us the elemental abundances. With me today is Martin Hoffman and Federico Tosi, and I'm going to give the wand here to Martin, and Martin will proceed. Martin?
Thank you. Okay. Well, I think we should understand Ceres a bit in the light of the goal of the Dawn mission. The Dawn mission is intending to gather information from the beginning of the planetary system. And this way, the framing camera images show the record of the surface processes over 5.5 billion years. In this respect, we see the traces of a living planet. There are specific reactions on external and internal influences. This you can see easily here on the first slide that I'd like to show you. So in the Ceres topography, we see a very complicated mixture of craters and other features. So the craters themselves are quite complex. And we see large curvilinear features extending from these craters, but also crossing them. All this is at this moment at low resolution that we have reached so far. Of course, not very conclusive, but only the first indication of what we might see in the future. And furthermore, we see some mysterious isolated high elevations, in fact very few of them, but there are some, with a steep slope. And this is here, the image shows one example. The brightness of the spot that is shown by a yellow arrow is only caused by the particular orientation into the direction of the sun. So this is illuminated much better than its environment just because of this steep slope. But anyway, this is a unique feature, and I must say what I have seen so far is different from what we have seen in similar terms on Vesta. All these things seem to be indications of a violent collision history. Well, to continue with the introduction of Ceres in the light of the goal of Dawn, Ceres has significance in the context of solar system planets, for it's larger by a factor of 2 than any other object between the orbits of Mars and Jupiter. These latter orbits are, or the distance of these latter orbits between Mars and Jupiter is 3 times the distance between the orbits of the innermost and the outermost terrestrial planets, that's Mercury and Mars. So it's quite a large volume that we talk about if we see Ceres in this area. And from its size, it's only 5 times smaller in diameter than Mercury, which itself is 3 times smaller than the Earth. But anyway, it's in a similar order of magnitude that we see already at Ceres. So it's not an asteroid. What we have seen so far or understood so far that Ceres in earlier years was called the largest asteroid. So we have to rethink these things, and in this light we have to understand our new data. What I want, many surface details. So on Ceres may look familiar from different other solar system objects, but they may have a quite different scientific meaning, and so many of the conclusions that look at first glimpse straightforward aren't that way, and many of these things that we see can only be treated by work hypothesis, and anything that we should tell you during this conference should be understood in that direction, that many things are really only preliminary. So let me continue. There's something. Yeah, so let me compare the two main targets of the Dawn mission, Vesta and Ceres. They are in size not so different, but if we look at the surface, they are really different. Vesta has mostly over its surface a higher reflectance, but much diversity. And we have a basaltic surface, and furthermore, on the surface we see various exogenous projectile materials. On Ceres, on the other hand, we have mostly very low reflectance, and it's basically consisting of carbonaceous chondrite-like surface, but there are locally yet unidentified buried material sites. To go more into details, what this means, you should see the framing camera false color mosaic that I'm going to show you here. So this is intentionally really shown as a false color image. So the reddest parts are in fact, if you would see them by human eyes, more bluish on a general pretty gray surface, and the bluish parts on this mosaic have really more light contribution from the redder parts of the visual spectrum. In any case, what was a real surprise to us is that the surface is not that uniform as a primitive carbonaceous chondrite-like surface should be. So we have very much variations on colors and albedos over the surface, on this superposed to very diverse surface topography, partly very rough, rich in craters, and other areas pretty smooth and poor in craters. So there's much to learn in the future. Now, talking about these materials, of course, one of the most prominent ideas that we have so far is that we don't see much external material, contrary to Vesta so far, at least at this resolution. And this is yet another mystery about Ceres that we have to solve. So this, I think, should be the first idea of what the surface looks like, and more on the details of the materials will be shown to us in the future, and also somewhat in the present, by the VIR instrument. And this brings me to my colleague.
Yeah, before we turn that off, could Federico point to, with the pointer to the bright spots where the that's where the two bright spots are seen in that region there, and then region 1 bright spot, and so there's the other one that we'll be talking about.
Yeah, there's another bright spot slightly above this, just at the limb, at the border, up here. This has also puzzled us so far because it has not been discussed so far by the earlier Hubble spacecraft images, and it has a similar behavior, let's say, in several respects, as the brightest spot that we have already known since the very first approach images.
Okay, thank you. Federico?
So good afternoon, everybody. I am now going to speak a little bit about one of the DON's remote sensing instruments, which is VIR, the Visible and Infrared Mapping Spectrometer, which is a high-resolution spectrometer in the broad spectral range covering the visible and the near-infrared range up to 5 micron. You can see here a picture of the instrument at the end of the on-ground calibration campaign carried out 10 years ago. VIR was built in Florence by the Ceres ES facility. It was funded and is also currently coordinated by ASI, the Italian Space Agency, and is operated under the leadership of INAF, Italy's National Institute for Astrophysics. So what is VIR and why VIR is on board DAWN? One of the main scientific drivers to have VIR on board DAWN was the inference of the surface composition of the targets as inferred essentially from spectroscopy. And this is achieved by VIR by acquiring very peculiar images, which are called hyperspectral images or cubes. Those images are acquired at the same time in a very large number of wavelength or spectral channel, covering the broad spectral range from the visible to the near infrared. So we can think about observing the scene in a total of 864 colors at the same time, which is very different from a regular framing camera. And so we might want to see our target at a given specific wavelength, or rather, we may want to focus on a pixel, on an element of the image or a region of interest and have the whole spectrum of that element or region of interest in the overall spectral range from the visible to the infrared. While the spectral resolution of VIR is fixed once and for all because it's an instrumental parameter, the spatial resolution, which is what we need to unveil details, essentially depends on the altitude over the surface. And in the case of Ceres, VIR will be able to see the surface of the target with a spatial resolution in the overall range from 25 kilometers per pixel down to 200 meters per pixel in the final phase of the mission. So here is one example of the very first hyperspectral image of Ceres that was acquired by the VIR instrument back in January 13 this year, from a distance of about 383,000 kilometers from the surface, yielding a spatial resolution of about 25 kilometers per pixel. In the foreground, you see an image as seen at one visible wavelength. The other image in red is instead the image of the same target from the same data cube, the same hyperspectral image, this time sampled at an infrared wavelength, which is representative of the thermal emission of the surface of the emission of the surface of Ceres in such a way that dark red tones are related to cold temperatures, whereas yellow and whitish tones are related to warm temperatures. So we can use VIR essentially as a compositional mapper, but also as a thermal mapper. In the next slide, you see a nice optical mosaic of the surface of Ceres as it has been derived by the framing camera, which was the instrument which Martin spoke about previously. And we have briefly touched the fact that on the surface of Ceres there are peculiar sites represented in particular by high albedo unit or bright spot. Those bright spots were actually seen before on the basis of albedo maps derived by the Hubble Space Telescope. And so there are at least two prominent spots which are here labeled spot number 1, located in the equatorial region close to the prime meridian, and another spot which is tagged spot number 5 or feature number 5, which is essentially made up by two distinct and separate, extremely bright spots. Those are by far the brightest spot seen on the surface of Ceres. So when we looked at the surface of Ceres with the VIR mapping spectrometer, we were able to see the spots as well. In this three-panel representation, what you can see on the left is a color image obtained on the basis of VIR visible data from a distance of about 45,000 kilometers, yielding a spatial resolution of about 11 kilometers per pixel. And the wavelength to build this composite image were chosen so as to be as close as possible to true colors, that is the colors that the human eye would see. So yes, the surface of Ceres is overall dark and brownish, but still you can see spot number 1 or feature number 1 highlighted by the white circle standing out with respect to the rest of the surface seen under similar solar illumination. In the middle panel, we have another composite image, which this time is made on the basis of infrared wavelength sampled by the VIR instrument. In this case, for example, the red corresponds to 1.6 micron, the green is 2.0 micron, and blue is 2.4 micron. And with this combination of colors, the surface of Ceres is overall very homogeneous, but still the bright spot, which is seen in the left image, can be recognized as showing slightly different colors with respect to the rest of the surface. We see here an orange to light pink color, which might be, in principle, indicative of a different surface composition or for example, different surface weathering taking place in that region with respect to the rest of the surface. But the biggest surprise came from the third image in the right panel. Once we exploit the thermal infrared wavelength range measured by VIR in order to retrieve surface temperature on the for the surface of Ceres, what we have found is that the bright spot number 1 actually corresponds to a dark spot in the thermal image, which means cooler with respect to the rest of the surface seen at the same time of the Cererian day and under the same solar illumination condition. And because we are far from the terminator, we are actually quite close to the subsolar point here, we can safely rule out that this is due to local solar, to the local topography combined with the solar, instantaneous solar illumination. When we move to the next slide, we have a similar three-panel comparison regarding spot number 5, and I remind you that spot number 5 is the brightest on the Ceres surface. VIR was still able to spot, despite the relatively coarse spatial resolution, was still able to identify spot number 5. Of course, Vir is not able to resolve the 2 distinct spots. But the surprise here comes from the fact that from a thermal perspective, spot number 5, at least with this spatial resolution, show no distinct thermal behavior with respect to surrounding terrains observed under the same solar illumination and at the same local solar time. So, for sure, we have bright spots on the surface of Ceres, which at least from a thermal perspective seem to behave in different ways, but one should keep in mind the fact that the Vir spatial resolution at the moment is still not high enough to disentangle whether this corresponds to a different surface composition or to a different structure of the surface material, for example, to a different thermal inertia driven by a different density of the surface material. So in the coming month, Dawn is supposed to also use Vir data to unveil the surface composition of the uppermost layer of Ceres surface down to depth of tens of microns. So we will learn something new about minerals, organics, possibly ices, and whatever is expected or presumed to exist on the surface. And we will also be mapping surface temperature with an increasingly high spatial resolution, so that we will get more and more insight about the surface processes going on Ceres. Thank you.
Thank you, Federico. Barbara, are you going to take questions now?
Yes, of course. Thank you very much for the very interesting data that you've shown us here today. We'll now open the floor for questions. Please say your name and affiliation and who the question is for. Anyone has any questions?
Hi, Jonathan Amos, BBC News. Just going back to the colour map, I mean, what does that tell us? What is that indicative of, the different colours? Is it texture, composition, just morphology? What do we get from that map? What does it tell us about Ceres?
Yeah, basically, of course, this is reflecting the distribution of materials that we see, but in this case, from the framing camera data, these different materials cannot be identified uniquely. For these, we need also the infrared data. On the other hand, the different albedos and also some of the color changes that we see are also related to the differences in the grain sizes and, of course, to in some few cases maybe also to some unidentified geometric effects because these should generally be cancelled out.
Okay, so it's composition, it could be the
Mostly.
texture of the surface.
Yes.
But there could also be light plays, light, just the way the light's bouncing off particular shapes on the surface.
Mainly
the
the
shape
size. Is it mainly the size?
I think it's mainly the composition and all other effects are secondary things.
Yeah.
Yeah, and you'll get the composition from later measurements when you get in very, very close.
That's right.
Basically, yeah. Okay. And can I just take you back to your talk this morning, just to be clear what you were saying about as Ceres rotates across the view, you see a change in brightness of the spots. Right. You kind of joked this morning that the spots were turning off as they went towards dusk. What did you actually? Can you just explain to me what you were describing this morning in the talk?
Yeah, of course, it suggests something, but I was a little bit cautious not to word this too firmly. You see, it looks like there's a dependence on the insolation, on the solar irradiation, and this is only the indication by the geometric facts that we see. But of course, we have to see this in terms of the resolution of the surface feature that we see in that area. This is at this moment only very coarse. There's an indication that this bright material is located somewhere in a depression. But in general, also this will have some impact, of course, on anything that's related to solar radiation. And we are really looking forward what the details that we seem to see at this moment will turn out in reality of greater resolution.
So what, it's sun angles?
Yes.
Yeah.
Thank you. Mariette Leroux, I'm a journalist with AFP, the French
Pardon?
news. I'm a journalist with AFP,
Yep.
the French news agency. Have bright spots like these ever been seen anywhere else in the solar system? And do you have any theories as to what they might be? I mean, why are they of such interest to you? Why do they intrigue you so much?
Well, there are, of course, several possibilities. Basically, you can say a bright spot on Ceres will be is potentially anything that's bright in the solar system. So, I don't want to go into more details, but I think there are some obvious things that are really bright, even today on the surface of the Earth and on other planets, and of course. I should remind you that very bright objects, as shown in the first part of the presentation, are very frequent in the outer solar systems. And in this respect, I think returning also to the talk that I gave this morning, we should see Ceres in a light just at the border to these outer parts of the solar systems, and of course then the causes of bright material in the outer solar system could be similar on Ceres, at least for these tiny spots.
Let me just add to that those spots are small compared to the other features that we're seeing around it. So we know that there's high albedo material in the solar system, but we haven't seen anything quite like that before. When we saw that, that stood out as different from the other planets.
This is a question from the chat from Alexandra Witzer for Nature for Federico. Can you talk a little bit more about why you think we're seeing differences between spot 1 and spot 5? Is it because they're made of different material?
So there is one very simple, very easy possibility is that as far as spot number 5 is concerned, because this is a very narrow feature, a very small feature on the surface, and we are currently considering VIR data with a relatively coarse spatial resolution of 11 kilometers per pixel. So one easy possibility is that we still don't have enough resolution to see it in the proper way. But as soon as we will get data with higher and higher spatial resolution beginning from the end of this month and especially May, we may be able to disentangle what is what. Because feature number 1, spot number 1, is broader, we don't have this issue because it's broad enough so that we can be confident about the fact that the measured temperatures are indeed real and indicative of something going on the surface. For example, in terms of roughness, of the size of the surface grains, for example, which might play a role driving a different thermal inertia and therefore driving a different instantaneous surface temperature. Whereas for spot number 5, we have to wait, but the current indication is that there might be bright spots on the surface of Ceres behaving differently, which is the takeaway message.
Thank you. Are there any more questions from here in the room?
Sorry. Just to clarify, this morning you said the color spectra of the spots, the brightest spots, was consistent with ice. So, I mean, how much ice is likely to be there? I mean, ice is not going to be stable at the surface, is it?
Yes, basically, if this is ice, of course, we cannot prevent it from being completely stable there. You're completely right in this direction. What I see is a spectral slope and distribution that's very similar with this, what we see, for example, on the surface of the Saturnian satellite Dione. From this, we cannot distinguish it by its shape. Its overall albedo is a little bit lower, but this could be the contamination from the overall dark material that we see on the surface. But as we don't see in the framing camera data any, let's say, typical water or ice absorption features, this is still a work hypothesis.
This is another one from the chat, following on from Jonathan's question. It's from Jacob Aaron from The New Scientist. Again, this one's for Federico. The thermal image of spot 1 looked pretty dark. Could it possibly be ice from a cryovolcano?
Well, we know that ice is cooler, is pretty normal. But we also know that temperatures overall, and this is a spot located in the equatorial region, are hardly compatible with large exposure of ice. So my feeling is that we are seeing here something which is not so strange and was seen before actually on Vesta as well. On Vesta we also observed a lot of high albedo, that is bright unit at the local scale, and most of those units, or a large number of those units, were exhibiting a different thermal behavior, being cooler. In that case, the bright units are indicative of a composition which is unaltered, that is less processed by space weathering effects. So before invoking cryovolcanism or something strange going on, we have to be prudent and rule out the easy possibilities and wait to have data with a higher increased spatial resolution, of course, that coupled with a good SNR is what we need to have a broader understanding of the surface composition and the temperature itself. What we can say here is that already at a broadly regional scale, there is at least one distinct thermal unit, and another bright spot seems to behave differently. That's all we can say today.
Thank you. We have time for one or two more questions, if anyone wants to ask one. Okay, if not, we'll finish here. You're welcome to approach the speakers and book one of the side rooms for interviews. And our next press conference, it's coming up at 2 on renewable energies and carbon capture and storage. Thank you.